Hidden deep beneath the massive layers of rock of the Swiss Alps, humans drilled through the mountains and excavated more than 28 million tons of geological material to create a railway line deep underground. This is the Gotthard Base Tunnel, the longest railway tunnel in the world, stretching for more than 57 kilometers. The tunnel runs beneath a mountain mass up to 2,300 meters thick, where natural temperatures can exceed 40 degrees Celsius, groundwater continuously seeps in, and geological pressure is powerful enough to deform massive tunnel boring machines. After nearly 2 decades of construction under harsh geological conditions, the tunnel opened a high-speed transport corridor between northern and southern Europe. In this video, join Mandarin Tech as we explore how Swiss engineers conquered one of the world's harshest construction challenges and turned it into an engineering marvel of the 21st century. Before the Gotthard Base Tunnel was built, trains crossing the Alps had to follow the old Gotthard route, continuously climbing, winding along the mountainsides, and passing through numerous short tunnels. This limited speeds while also reducing the transport capacity of increasingly long and heavy freight trains. Instead of continuing to expand the old route, Switzerland spent more than $12 billion to build an entirely new railway corridor beneath the base of the Alps. 2 single-track tunnel tubes were excavated in parallel through the mountain mass, with each tube carrying 1 railway track, creating an almost straight route with a much lower gradient than the old line. After 17 years of construction, the Gotthard Base Tunnel was officially inaugurated in 2016 and entered full commercial operation with continuous operating capability. Passenger trains can reach a design speed of up to 250 kilometers per hour, while long and heavy freight trains can cross the mountains with less locomotive assistance than was required on the old route. The Gotthard Base Tunnel has since become an important link in Europe's north-south rail corridor, shifting much of the transport traffic across the Alps deep beneath the mountains. To shorten the construction period, the project was divided into multiple work fronts, allowing engineering teams to attack the mountain mass simultaneously from different directions. But before the boring machines could enter the Gotthard Massif, the engineers had to find a way to ensure that excavation drives, starting from different locations, would still meet precisely after traveling tens of kilometers underground. On the surface, the entire tunnel alignment was established using a high-precision surveying network. GPS was used to determine the coordinates of the tunnel portals, vertical shafts, and intermediate access tunnels, creating a reference system for each construction section. Once the alignment had been established, the TBMs began advancing into the hard granite layers of the Gotthard Massif. Each system was more than 400 meters long and weighed around 3,000 tons, equivalent to a mobile factory lying horizontally underground. Because of their enormous size, the machines were manufactured in sections in Germany, transported to Switzerland, and assembled directly at the construction site. But once the machines moved deep beneath rock layers, several kilometers thick, satellite signals disappeared completely. From that point onward, the TBMs were guided by an underground surveying system. Engineers used laser theodolites aimed at measuring targets mounted on the machines to continuously determine the angle, distance, and position of the cutterhead. Small deviations were detected early, allowing operators to correct the machine's direction before they accumulated into larger errors. At the front of each TBM was a cutterhead nearly 9 meters in diameter, fitted with 58 steel discs. As the cutterhead rotated, each disc pressed against the rock face with forces reaching tens of tons, creating a network of fractures and crushing the mountain rock into smaller pieces. The excavated rock fell into a collection system and was carried through the machine by conveyor belts to the rear, while the hydraulic system continued pushing the TBM deeper underground. After each excavation section, the machine's position was checked again, and new survey points were established along the tunnel walls. This chain of coordinates continuously guided the cutterhead along the designed tunnel centerline. Under stable geological conditions, a TBM could advance between 10 and 30 meters per day, averaging around 15 meters in 24 hours, while operating continuously across 3 shifts. Immediately after the cutterhead opens a new section of tunnel, the newly created space must be reinforced before the surrounding rock has time to crack or shift, While the front of the TBM continues crushing rock, another system behind it immediately stabilizes the tunnel crown and walls. Because the Gotthard project uses gripper TBMs in hard rock sections, the support system does not rely on precast concrete rings installed directly behind the Cutterhead. Instead, the level of reinforcement is adjusted according to the geological conditions at each location. First, steel rock bolts are drilled deep into the surrounding rock to connect layers at risk of separating with more stable rock farther behind. In areas with numerous fractures, steel mesh is added to hold back smaller rock fragments that could break loose. Next, shotcrete is sprayed directly onto the tunnel crown and walls, following the uneven rock surface before hardening into a continuous protective layer. When rock quality deteriorates, the density of the rock bolts is increased, and steel arches can be added to control more severe deformation. TBMs were used to mechanically excavate most of the two main tunnel tubes. However, in areas with weak geological conditions and high pressure from the surrounding mountain mass, the machines were no longer a suitable option. In areas with unstable geological conditions, if a TBM entered these zones, the surrounding rock could squeeze the machine and leave it permanently trapped. Therefore, engineers had to stop the machine and switch to the traditional drill and blast method. First, the rock face was stabilized by injecting concrete into the fractures. Metal rock bolts, several meters long, were driven deep into the mountain mass to connect loose rock layers with the more stable ground behind them. Next, a 60-ton jumbo drilling rig moved up to the excavation face. Its electro-hydraulic arms simultaneously drilled a series of holes 3 to 4 meters deep according to a precisely calculated pattern. Instead of traditional dynamite, the site used modern emulsion explosives. The components were transported separately and mixed only at the excavation face, reducing the risk of accidental detonation. Once workers and equipment had withdrawn to a safe area, the charges were detonated in a sequence separated by a few thousandths of a second. The central blast created the first void, while subsequent blasts progressively broke the surrounding rock outward, reducing vibration and producing fragments small enough to be transported. After each blast, the ventilation system had to remove dust and toxic gases. Excavators then moved in to clear the broken rock. The excavation face was inspected, and the entire cycle began again. This method advanced only a few meters per day. Although these geological zones accounted for only a small portion of the total route, crossing them took nearly as long as many of the other sections combined. Here, progress was no longer determined by the power of the machines, but by the ability to read and control every movement of the mountain mass. After the rock mass had been stabilized, work shifted to constructing the tunnel's permanent structural lining. On top of the initial support layer, workers installed a drainage system and covered it with a waterproof membrane. The membrane sheets were sealed together to prevent groundwater from penetrating the inner structure. Formwork was then moved into each section, and concrete was poured continuously to create a smooth and solid inner lining, designed to protect the tunnel throughout its service life of approximately 100 years. The completed sections gradually transformed the rough rock surface into a tunnel with precise geometry. While the tunnel lining was being completed, the excavation drives continued advancing toward each other. On October 15, 2010, after 14 years of drilling, blasting, and crushing rock, the Cutterhead of a TBM broke through the final meters. As the rock separating the two sections collapsed, the construction teams saw each other for the first time inside the mountain. Once the concrete lining and connecting tunnels had been completed, the two tunnel tubes were still nothing more than empty corridors stretching beneath the mountain. To transform them into a high-speed transport route, a complete railway system had to be installed within the confined underground space. Pairs of rails, each 120 meters long and weighing more than 7 tons, were transported deep into the mountain by specialized trains. A tracked machine pulled the rails from the transport wagons and placed them onto temporary rollers. Once they reached the correct position, the machine lifted each rail onto its support system, while workers adjusted the elevation and alignment using fixed survey markers along the tunnel walls. The two rail ends were clamped inside an automatic welding machine, pressed together, and heated by a high-current electrical flow until the metal became white-hot. A powerful compressive force then pushed the two ends together, creating a continuous joint. Beneath the rails, hundreds of thousands of sleeper blocks were positioned by a gantry crane. With each lift, the equipment could place 60 blocks, forming the framework that held the rails at the correct elevation and at an inclination of 1.45 degrees. Concrete was then produced directly inside the tunnel by a specialized mixing train and transported to the pouring point within approximately 20 minutes. Workers compacted the mixture to remove air bubbles, then manually finished the surface with a transverse slope to direct water toward the drainage system. Every meter of track was measured again before handover. Above the rails, the contact wire system was fixed to the tunnel crown using tens of thousands of anchor points. The wire had to be maintained at the correct height and tension so that the pantograph on top of the train could remain in stable contact while the train traveled at high speed. Electronic positioning markers along the track continuously determined the position and speed of each train and transmitted the data to the control center. Once the railway tracks, power supply system, and control network had been installed, Gotthard still could not immediately begin receiving commercial trains. The entire project had to undergo an extended testing phase, during which every system was operated under conditions as close to real-world operation as possible. Specialized trains moved slowly through each section to measure vibration, track bed stability, and the response at the turnouts. Speeds were then gradually increased, allowing engineering teams to detect even minor deviations. The overhead contact wire system was also continuously monitored. Sensors recorded wire tension, the amount of uplift as the pantograph passed beneath it, and the system's ability to supply stable power to the train. Meanwhile, the signaling network had to accurately determine the position, speed, and distance between trains inside the two tunnel tubes. After years of mountain excavation, concrete pouring, and installation work, the Gotthard Base Tunnel was inaugurated in June 2016 before officially entering commercial operation on December 11th of the same year. The first trains entering the tunnel marked not only the completion of a major engineering project, but also the opening of an almost level railway corridor through the heart of the mountains. The Gotthard Base Tunnel does more than simply shorten the journey across the Alps. By lowering the railway route closer to the base of the mountains, Switzerland eliminated many of the steep gradients and curves that had limited the capacity of the old Gotthard line. The new route is approximately 30 kilometers shorter and can accommodate up to 260 freight trains and 65 passenger trains per day, compared with a limit of around 180 freight trains on the former mountain route. For freight transport, the impact goes beyond speed. The almost level route allows longer and heavier trains to cross the Alps with fewer locomotives, reducing shunting operations and consuming less energy. Gotthard has therefore become one of the most important pieces of infrastructure in Switzerland's strategy to shift transalpine freight transport from road to rail. Today, around 70% of freight crossing the Swiss Alps is transported by rail. For passengers, Gotthard, together with the Mandarin Base Tunnel and the connecting routes, has brought northern and southern Switzerland closer together, reducing travel time along the north-south corridor by up to approximately 1 hour. More importantly, the Gotthard Base Tunnel demonstrates an entirely different way of overcoming extreme terrain. Instead of forcing the railway to conquer the mountain, engineers moved the entire transport route beneath it, transforming the Alps from a barrier into a link in Europe's transport corridor. The Gotthard Base Tunnel is a powerful example of how a massive natural barrier can be transformed into a vital link between nations. Today, it serves as a central part of Europe's north-south rail corridor, connecting major economies from Germany and Switzerland to Italy and the Mediterranean region. Goods, passengers, and economic activity can now move through one of Europe's greatest natural obstacles with almost no need to climb the mountains. What megaproject do you think could surpass the achievement of Gotthard in the future? Share your thoughts in the comments below, and don't forget to subscribe to Mandarin Tech to discover more engineering projects that are changing the world.